Hello, this is our fourth lecture of this series on photochemistry, organic photochemistry. We have already talked about some introductory part on involving principles of photochemistry. We have discussed about photochemistry of alkene, different examples of cis-trans isomerization, and some examples cis-trans isomerization followed by cyclization. We have also discussed about the photochemistry of 1,4-diene, which undergoes interesting photochemistry to give undergo dipymethane rearrangement to give vinyl cyclopropane as one of the product. So it has attracted a lot of attention due to the construction of three-membered highly strained system. Several examples have been reported and we have also discussed few of them. Now going to the photochemistry of 1,5-diene. Here 1,5-diene and later on we will also discuss photochemistry of carbonyl compounds. As far as 1,5-diene is concerned, this is the basic skeleton of 1,5-diene. We have 1, 2, 3, 4, 5 and 6 carbon system, two double bonds between carbon number 1 and 2, and second double bond between carbon number 5 and 6. So this is a basic skeleton 1,5-diene. We would like to see how this 1,5-diene undergo photochemistry. If we look at this particular skeleton of 1,5-diene under thermal condition undergo well-known 3,3 sigmatropic shift and also known as Cope rearrangement, and then and giving rise to this product. So if we number this 1, 2, 3, 1 dash, 2 dash, 3 dash, so it is a concerted reaction, one-step reaction where there is a cleavage of bond between 1 and 1 dash takes place, and the construction of a new bond, sigma bond between 3 and 3 dash takes place, whereas the double bond now is created between carbon number 1 and 2 and 1 dash and 2 dash. But if it is now is more or less both are same, because if it is unsubstituted but we will see some example with the substituents on this particular diene and see how it. So this is a well-known 1,5-diene under thermal condition undergo well-known 3,3 sigmatropic shift, also known as Cope rearrangement, to give this one of the product. Whereas on the other hand, this 1,5-diene under photolytic condition undergoes 1,3 sigmatropic shift, and so if we number this 1, 2, 3, 1 dash, 2 dash, 3, so there is a cleavage of this bond and shifting of this double bond takes place to give this as the this as the product. And you can see here the new double bond is created between carbon number 1 and 2, and a new sigma bond is created between carbon number 1 dash and 3 dash, and a new double bond is created between carbon number 2 dash and 3 dash. So so in principle 1,5-diene undergo 3,3 sigmatropic shift to give this product, whereas under photolytic condition it undergoes 1,3 sigmatropic shift to give this one the product. Since it is unsubstituted, both are same product, but now let us see with the substituent. If we put the substituent on this, say for example, if we have a substituent Z here, this is also a 1,5-diene system. 1, 2, 3, 4, 5 and 6 basic skeleton, 2 double bond between carbon number 1 and 2, another double bond between carbon number 5 and 6, and the position is 1, 2, 3, 4, 5 is a 1,5-diene. And if we number this 1 dash, 1, 2, 3, 1 dash, 2 dash, 3 dash, so under photolytic condition we have just now mentioned in the previous slide that it undergoes 1,3 sigmatropic shift. Here Z is the substituent, Z is a substituent where Z could be a phenyl group or it could be an acyl group, RCO. RCO. And then now under photolytic condition, it undergoes 1,3 shift to give this as the product 1, 2, 3, 1 dash, 2 dash, 3 dash. Now you can see the substituent which was on the carbon number 1, now it is, and it was connected to a saturated carbon. Now after the rearrangement, it has the substituent now is at the unsaturated carbon and carbon number 1, and now this is, and the so now this is a new product after the rearrangement. And so just to mention that 1,5-diene under photolytic condition undergoes 1,3 sigma tropic shift to give this one of this as the photo product. Not many examples are known here. One of the examples which is reported in Turo's book is shown over here. This is a diene system once again with a cyclohexane ring. So you have a basic skeleton is 1, 2, 3, 4, 5 and 6. This is a basic skeleton, 1, 6 and the carbon and 2 double bonds. One double bond is carbon number 1 between carbon number 1 and 2, a second double bond between 5 and 6, and position is 1, 2, 3, 4, 5. This is a 1,5-diene system, and we know that under thermal condition 1,5-diene undergo 3,3 sigma tropic shift, which is known as Cope rearrangement. And in this rearrangement we see a concerted reaction like this, where there is a new sigma bond is created between carbon number 1 and carbon number 6, and a new double bond is created between carbon number 2 and carbon number 3, and sigma of course here we have this is 4 and this is 5. So this is after thermal condition, and under photolytic condition we know that it goes via and it goes 1,3 shift. So we have like this rearrangement. A new double bond is created between carbon number 2 and 3 after photochemical 1,3 sigma shift. 1,5-diene undergoes 1,3 shift under photolytic condition to give this as one of the product. The double bond, a new double bond between carbon number 2 and 3, a single bond between carbon number 1 and carbon number 3. This is the shift. And then we have of course 4 and this goes like this. This is 3 and this is 4, this is 5 and this is 6. So these are the two products after thermal reaction as well as after photolytic condition. This is going after 3-3 shift, this is going after giving after 1-3 shift. So these are the few examples of so essentially photochemistry 1,5-diene undergoes 1,3 sigma tropic shift under photolytic condition, and these are the two examples where this Z is being the substituent as a phenyl, and RCO it gives this as the product. Is another example is this one where there is a presence of a cyclohexyl group is the part of this 1,5-diene. So this is the product after. After this we move to photochemistry of carbonyl compound. Carbonyl compound have been very well studied. Lot of examples have been reported in the literature, and let us see how we look into this and what type of photochemistry is shown by carbonyl compounds. In the next coming slides, we are going to discuss about the photochemistry of carbonyl compounds. Carbonyl compounds, intramolecular reaction of carbonyl compounds, saturated carbonyl compounds, alicyclic systems, alpha beta unsaturated compounds, beta gamma unsaturated, alpha beta unsaturated, photochemistry of cyclohexanone, intramolecular reaction of cycloaddition of alkene with carbonyl compound, dimerization and oxidation formation. These are the few examples which we are going to discuss in this under this topic, the photochemistry of carbonyl compounds. As I mentioned, is a well studied. Carbonyl compounds have been extensively studied. It has strong absorption in the region between 230 to 230 nanometers. It undergoes 4 different types of photoreaction. First one is norrish type 1 reaction. It is mainly, which is nothing but is alpha bond cleavage. Is very common in aliphatic aldehyde, aliphatic carbonyl compounds, as well as alicyclic system like cyclohexanones, cyclopropanones, cyclobutanones, and so on and so forth. Second type of reaction which is reported in the case of carbonyl compound is norrish type 2 reaction, which involves intramolecular gamma hydrogen abstraction. So whenever there is a position of gamma hydrogen, the excited carbonyl can abstract the gamma hydrogen to give a 1,4 diradical species. So this and then this 1,4 diradical once again combine to give a norrish type 2 reaction to give a cyclobutanol as one of the product. So this is extremely important product, because again here if we are constructing a highly strained 4-member ring system, which is not very easy to form and has a lot of attracted synthetic examples to see that such reactions by taking a suitable starting material to give this norrish type 2 reaction where there is availability of gamma hydrogen. So norrish type 1, norrish type 2, both are very common in aliphatic carbonyl compounds. A third type of reaction is photoreduction, means reduction of carbonyl compounds is also common in aromatic carbonyl compounds. So carbonyl gets reduced to CHOH. So this is has been known as in the case of aromatic like benzophenone and carbonyl gets reduced to give the corresponding hydroxy derivative. A fourth type of reaction is the cycloaddition of carbonyl compounds with alkene to give a 4-member oxygen containing heterocycle, that is oxetane formation. This also has very important, because in this one a 4-membered ring with a heteroatom is constituted and also plays an important role in the stereochemistry of the starting alkene and in the stereochemistry of in the product formation, whether the stereochemistry is retained or stereochemistry is going to reverse, and under what condition how stereochemistry is going to differ in the product formation of oxetane when the carbonyl compound reacts with alkene. So now let us see one by one few examples of one of these 4 type of reaction. That is, first one is norrish type 1 reaction, where we have mentioned that is involves alpha bond cleavage. This is an aldehyde. R is an alkyl group. It can have a methyl, ethyl, propyl, and so on and so forth. And under photolytic condition, it goes type 1 reaction, which is nothing but alpha bond cleavage. These are the 2 alpha bonds. So it can cleave either this or this. So it has been shown by cleaving both in this bond cleaving to give you a R radical and then acyl radical. If this bond cleaves, gives the hydrogen radical as well as acyl radical RCO. So This is the first step where the light is required. So when we have a aldehyde, it undergoes, under photolytic condition, it undergoes alpha bond cleavage, which is known as Norrish type 1 reaction, and then to give you acyl radical as one of the main intermediates in this reaction. These acyl radicals are known to undergo very fast loss of carbon monoxide minus CO to give an hydrogen radical again here, and then from this loss of CO gives to alkyl radical. So, and then this once again can combine, this radical can combine with R dot to give you RH. This RR can combine to give you give RR, and then this can self combine. So there is a possibility of 3 types of combination. 2H dot can give HH, H dot can combine with R dot to give HR, RR2R can combine to give RR. So these are the 3 products obtained from the cleavage of alkyl radicals. So we essentially end up with higher alkanes. Higher alkanes, hydrocarbons are formed as in the case of Norrish type 1 reaction of aldehyde. Here is the same thing. This acyl radical can undergo very fast loss of CO to give R dot, and then recombination of these radicals to give RR, RH or HH combined to hydrogen radical conversion. So these are the so essentially Norrish type 1 is going to give the higher alkanes, corresponding hydrocarbons, and so on. So the first step is the alpha bond cleavage. Whenever you have an aldehyde, aliphatic aldehyde, especially under photolytic condition, it undergoes alpha bond cleavage. Alpha bond is the bond next to the carbonyl. It can and hence this alpha bond cleavage can give you R radical and acyl radical, or H radical or acyl radical, and then this acyl radical is very fast susceptible to undergo loss of CO to give you R dot or H dot, and then which once again this recombination of these radicals to give you to give rise to hydrocarbons or higher alkanes. So this is the this is in this one we have talked about photochemistry of aldehyde. This is a Norrish type 1 reaction of aliphatic ketone. When you have an R1 and R2, where you have a different substituents. For example, you have a CH3, C double bond O, CH2, CH3, or you can have, if R with both R and R1 and R2 are same, then we have acetone. If and hence if you can have a different R1 and R2, then you have a methyl ethyl or ethyl propyl, and so on and so forth. So under photolytic condition, this in aliphatic ketone can go type 1 reaction, or Norrish type. It is known as Norrish type 1, which is nothing but alpha bond cleavage. Alpha bond cleavage, I have mentioned the alpha bond cleavage is this bond next to the carbonyl. So we have shown the cleavage of both the if R1 and R2 are different, then of course it is going to give you 2 different alkyl radicals. So we have shown it can definitely either cleave this and or cleave this. Of course the also depends upon the stability of alkyl radical as well. More stable radical will form first, but still other possibilities we cannot rule out. So we have shown the cleavage. If this R1 and carbonyl bond cleave to give you R1 dot radical, alkyl radical R1. This is acyl radical. This acyl radical we have just now shown that undergo very fast decarbonylation to give you R2 dot. If this bond cleave takes place, then we have R2 dot, then R1 CO radical undergoes decarbonylation to give you R1. So essentially this aliphatic carbonyl compounds can undergo alpha bond cleavage to give you acyl radical and alkyl radical. Acyl radical undergo very fast decarbonylation to give you once again alkyl radical. So this can combine to give self combination to give you R2 R2, or it can combine these two to give you R2 R1, or this can combine to give R1 and R1. So essentially you can see with the aliphatic ketones can give higher alkanes. So we start with acetone, we get ethane. If you start with this butanone, we get we can get ethane. Of course, we have combination of this ethane, combination of butane, and combination of ethyl and then propane. So you have ethane plus we have propane, or we can have a combination of this ethyl plus CH3, CH2, CH2, CH3. So you can see these three different types of products are formed from this as being the starting material, that is 2-butanone. To give first step will be alpha bond cleavage, is a type 1 reaction, give acyl radical, very fast decarbonylation to give you alkyl radicals, and which can once again undergo self-time combination. This is another example of we have a dibenzyl ketone, under photolytic condition. What are the different steps, what is the product, and so on and so forth. So if somebody asks you, so we have to analyze very carefully the starting material. This is you can consider this because not carbonyl, benzene is not directly connected to carbonyl, so it is CH2 carbonyl, again CH2 carbonyl, so it can be considered as a aliphatic ketone. So we know that under photolytic condition aliphatic ketone undergo type 1 reaction, which is nothing but alpha bond cleavage. So there is a cleavage of this or this or this. It gives you we're going to give same because it is a symmetrical molecule. We have a benzyl group on the either side, so it is going to give a similar radical. So this can give C6H5 CH2 C double bond O radical plus CH2 C6H5 radical. So this is the first step involved in this the alpha bond cleavage, and then this can very fast undergo decarbonylation to give C6H5 and CH2 radical. And now we are going to recombine this. This can recombine to give C6H5 CH2 C6H5. So this is one of the photo product in this particular case. Is the same thing has been shown over here. What we have, so this under photolytic condition is alpha bond cleavage type 1 to give this diradical species, decarbonylation of this acyl radical to give this, and then coupling of these two give this product. So these are the few examples of aliphatic aldehyde and aliphatic ketones. As I have mentioned, the cycloalkanones or alicyclic ketones or alicones such as cyclopropanone, cyclobutanone, cyclopentanone, cyclohexanones, and all related system may also undergo similar type of reaction, that is type 1 reaction under photolytic condition, and can also undergo type 1 reaction, which is nothing but alpha bond cleavage. Alpha bond is the bond next to the carbonyl. This is alpha bond. This is also alpha bond. That's what we have seen in the previous slides. Type 1 reaction of aldehyde, type 1 reaction of ketone, and now we are going to see a few examples of type 1 reactions of cycloalkanones, that is alicyclic ketones, and so on. And now this is the one of the example, cyclobutanone under photolytic condition H nu can undergo type 1 reaction. Type 1 reaction is nothing but is alpha bond cleavage. So you can cleave, this is alpha bond and this is also alpha bond. You can cleave either this, or you can cleave, if you cleave this you get this one, or if you cleave this you get, or you can give this. So both are both the radicals are same, because there is no substituent on the alpha position. So it is you are free to cleave any one of this. So this is the shown. Now this is the main intermediate after the attack of photon, giving rise to acyl radical. This undergoes 3 different type of reactions. So as compared to aliphatic ketones, the photochemistry of alicyclic ketones are slightly important in such a way that there are different pathways open for the photochemistry of alicyclic ketone. First step, we have already seen decarbonylation, loss of carbon monoxide to give you this diradical. This as a diradical, and then this can combine to give you cyclopropane as one of the products. It is also possible that it can abstract a hydrogen atom, and then there is a formation of a double bond. So you can there is a possibility of formation of alkene. So one route is open for this intermediate is the first decarbonylation to give you 1,3-diradical. 1,3-diradical can combine to give cyclopropane as one of the products, or it can also give alkene by abstracting hydrogen atom by one of the radical to give this alkene. Path B is the beta bond cleavage. This radical is shown in the next. This is called beta bond cleavage. This is alpha bond. This is alpha bond. This is beta bond. This is alpha bond. This is beta bond. So beta bond cleavage can take place to give you alkene as one of the neutral products, and then ketene as the other product. So the path B is the beta bond cleavage. This bond cleavage takes place to give an alkene as well, and then ketene as the intermediate. We know that the ketene is highly unstable, and it can immediately undergo decomposition in the presence of water to give a carboxylic acid, or ethanol, or an alcoholic solvent like ethanol and methanol being the solvent, can give an ester. So this is the second route for the cleavage of this acyl radical. Path 1 and then path 2 is the beta bond cleavage to give an alkene and the ketene, alkene and ketene as product, and then which can lead to an ester. Path 3 is the ring. This is very important in the sense that it undergoes ring expansion. Ring expansion route. Ring expansion route. This radical can attack on this, and then this gives rise to carbene as the intermediate. Carbene as the intermediate. So and then this carbene can, in the presence of a alcoholic solvent, can give again the this is HNOR. So this is the, so in the case of a third route for the photoreaction of cycloalkanone is the ring expansion products, as cyclobutanone is going to give you a 5-membered oxygen containing product, and this is again very extremely important from synthetic point of view, because the oxygen which is a part of the carbonyl, now it is a part of the ring system. The formation of this product can be visualized as, so this is the intermediate, this one. Now this radical can attack here, and then this can double bond can go. So there is a new bond formation to give a so you have this one. Is a new bond formation, and no, of course there is no double bond. Okay. Okay, I'll just put it here. Just so this is the diradical. This can attack here to give this, and then oh, okay. Let us once again do it here. Okay. So we just want to see how this route works. We are just this is the diradical. After alpha bond cleavage, this radical attacks on this carbon, followed by shifting of the double bond to give a this is the carbene intermediate, and then this in the presence of alcoholic solvent can give rise to HOR. So this is so as just to summarize here, the cycloalkanone undergoes three different types of photoreaction. First step is the as usual. So just to see once again how it works. Okay. Right. Cyclobutanone under photolytic condition can give rise to alpha bond cleavage to give you 1,2 diradical. 3 pathways are open for this A, B, C. Path A is the decarbonylation to give you cyclopropyl radical. 1,3 radical can combine to get cyclopropane and alkene. Path B is beta bond cleavage. So this can take place only in the case of cyclobutanone. Higher rings, it may not lead to loss of neutral molecular alkene. This ketene formation in the presence of alcohol will give an ester. Third pathway is the ring expansion. This radical can attack on this, and then the carbene formation, carbene. and then this decomposes in the presence of to give an ester. So again, the photochemistry of cycloalkanones have attracted enormous amount of interest, and several examples have been reported in the literature. Due to the fact that when the, say for example, this is the cyclobutanone, if one of the carbon is substituted, say for example, you have this one, the substituent, this is now if we shine light, this is a alpha bond, this is also alpha bond. There is a possibility of two intermediate. If this is a type 1 reaction, alpha bond cleavage. If we cleave this, we get is the tertiary radical. If we cleave this, we get so these two radicals are possible under photolytic conditions. Tertiary is primary, and we know that the more stable radicals are formed in the reaction, which leads to the product. So this is going to form and this is going to not form. So whenever the alpha carbon is substituted with the methyl group, there is a preferential cleavage of alpha bond, and so preferentially this bond cleave to give you a tertiary, because this side, this radical is same in the acyl radical is going to be same in both the, but this carbon radical is going to play an important role. This is a primary carbon centered radical, this is a tertiary carbon centered radical. Tertiary carbon centered radical is more stable, it prefers to this preferential cleavage takes place. Now next few examples we are going to discuss about this. So we just stop here and continue on the next lecture. Thank you very much. In the next lecture, we are going to take a few substituted alpha carbon substituted cycloalkanones, and where it is going to give you preferential cleavage to give you more centered, more stable carbon centered radical. But this is again, it is not always. So we will see what are the exceptional cases where although it is more stable, although it is tertiary, but still it doesn't form and it is preferred to cleave primary. Okay, so we are going to discuss a few of these examples. Thank you very much.